Okay, let's keep going. Pulling it all together. Vectors 4. What I'm going to do is split this one up. We're going to look at individual vectors, one vector at a time now. That will build our skills so that we can add and subtract vectors. That's what we're really building up to, one thing. So we have to take vectors, and we want to go from component form to polar form. I've got a few examples here I'll show you. It's really just triangles, you'll see. In the next video, we'll go polar form to component form. Also really good in just basic trig and triangles, but I'd like to do that separately. And then we'll add and subtract them. So, what I've got here are three vectors. So notice up here the displacement vector that I've written. Again, I could write that as d from 1 to 2 or delta r, change in position from 1 to 2. And I've given it, for whatever reason, I've got 3.0 meters in the x direction, whatever that is, minus 4.0 meters in the j hat, or the y direction. Okay, that's all that says. And the question I want to know, this is component form, I wanted to get it into polar form. That is, how much, how far away from 1 is 2? And in what direction? I don't know what the path was, but the displacement from straight from 1 to 2, how much and what way. One thing that I want to notice here is that minus 4.0 meters j hat is the same as plus 4.0 in the negative j hat direction. So we can write it either way, but minus means in the negative j hat direction. Okay, so let's take a look at that one and see how easy it is. The key to doing all this stuff is a sketch. Now you could do it very carefully. See over here I've done a grid. So I've created a grid. I could measure it carefully, I could use my angles, and I could literally get my answer simply from measurement. More often than not we'll do it through calculation. So I've got a displacement from 1 to 2. Now the beauty is, one thing that you realize, is that I'm going to be directed in the positive x direction 3 units, and then in the negative y direction 4 units. When you're talking about vectors and you analyze them, it doesn't matter where the object is. You can start this, you can put this anywhere you want. So you can kind of slide that vector over here. I'm going to start it, let's start it right here. What, I got 3 and I got 4, I'm going to go here. I'm going to start this guy here, state 1. And I don't know how I get there, but I'm going to go over to state 2 and work my way over to state 2. And how am I going to get there? Well, whatever the path, I go 3 units in the positive x direction. Now, I didn't say here, you see this grid, positive x could be that way. I'm going to go ahead and put plus x over here, plus x over here. All right? In fact, I'm going to do that in blue just to be consistent with my colors, not that it matters so much, right? Plus x. So plus x is to the right. I'm choosing, good and to left. Can you see all that? That's all good. And then I'll choose plus y to be up. And again, I could choose plus y to be down. All I have to do is clearly show it. So those are all the positive direction and the positive direction here. So if I go 3 in the x direction, that means I'm going to go 1, and I really recommend for components drawing them as dashed lines. 2, 3. Also key, if I don't put an arrow on that, I don't know which way that line's going. When you're drawing components, make sure that you put the arrow on the end. So this would be d 1 to 2 x, or d 1 to 2 x. A little clunky, but that's what it is. It's the component. And then I'm going to go down 4 units. So I'm going to go 1, 2, 3, 4. Again, I really recommend, this is only the part, this is not the whole thing, so that's why I use the dash part, right? So that would be d, not negative, but that's d1 to 2 y, which is equal to negative 4.0 meters. And dx is equal to 3.0 meters. Okay. So there I have it. Started here, ended here. So this is state 2. I really don't know how I got there, but the displacement is some this way, some that way. And so the total vector, which I draw as a solid, goes from here to here. Now, some people make this mistake. They kind of think of it as a circuit. And draw that as a solid line with an arrow. A lot of people make this mistake. It isn't as though you're going around. You're going from 1 to 2. You could get there going right and down. You could get there straight. You could get there any way you want. But your displacement, 1 to 2, is to the right and down. How much is that? Well, you see the triangle, right? Pythagorean theorem. So the length, how much, is going to equal dx squared plus dy squared square root. It's 3 squared plus negative 4 squared, or 4 squared, square root. That's how much this is. Now I could measure this. I could measure this and figure out the scale, how long that is, so how much it is. And then what about the angle? Well, I could give two angles, can't I? I could specify the angle. Either I could give this angle, or I could give this angle. Of course, that angle is the same as that angle. And the blue angle here is the same as this angle. Those two are the same. Now I could measure them if I drew it to scale. That's a nice little exercise. But usually we calculate them. What is the tangent of the blue angle equal to? It's equal to y over x. Delta y. Right? This is delta y. This is delta x. This is delta y, change in position. Kind of a nice way to write it. I like that. So the tangent of delta y over, getting too many colors here, delta x, sorry. That's where I'm going. Okay, well, let's write this. Let's name it. We need to name this. I'm going to call this guy alpha, whatever. Tangent of alpha is delta y over delta x. Opposite over adjacent. Therefore, alpha is the inverse tangent of delta y over delta x. However, delta y is negative. Highly recommend using absolute values, and I would get a number, the inverse tangent of 4 over 3, and then I would say that angle down from the positive x direction. Now I could just as well use this angle, and sometimes you call it theta. Okay, let's call this theta. Well, the tangent of theta is opposite over adjacent. Again, I recommend using absolute value. Opposite theta is delta x over delta y. Therefore, theta, that angle, is the inverse tangent of delta x, 3, over delta y, 4. Absolute value. Then I would say it's, one way to say it is, if you get, 38 degrees, then you'd say it's 30, that's 38 degrees, or that's 38 degrees. So that's how you tell the direction. Sometimes you show the picture. That's what the answer is. So how much is easy because these are perpendicular, so it's that squared plus that squared square root. The angle is a little bit tricky, but you simply have to use inverse tangent, and it's going to be the ratio of the components. It could be delta y over delta x, or it could be delta x over delta y. It doesn't matter, right? If this is 70, that's 20. So get either one, and then show it on your picture. Again, highly recommend using the absolute value sign. So what if I do something else? What if I talk about velocity and not displacement? Well, I can still put it on a grid, but now we're not talking about displacements, right? We're talking about velocity, and this gets a little messy here, right? But you can do it. And I'm going to take my vector, and I'm going to draw it on my coordinate system. The length of my vector, velocity vector, has to do with the speed, but I'm going to represent it as a length. And here I go, okay, fine, sorry for the mess. I got velocity 2 is 4 meters per second in the negative x direction, and 10 in the positive y, so that's going to go up. I'm going to start it down here so I can go up. All right, so and it's going to go to the negative, I'm going to start it over here. Start that V2 over there, and I'm going to go, well, it's not a length, this is meter per second, it's a speed, but I'm going to represent it as a length. I'm going to go over 4 in the negative x direction, that's all it says, dash, 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 1, 2, 3, 4. Put an arrow, that's V2x, right? And then 10 meters per second in the positive y direction. Hopefully I can get that, I'm not sure I can fit that in there, let's see. I got 1, 2, 3, 4, 5, 6, oh my goodness, right? And putting an arrow on it. So I have an easy fix for that. 1, 2, 3, 4, 5, 6, I like that. Great, I'm going to change my example, 6.0. Good. Now that's what that is. All right, so I've drawn my components as dashed lines with tips on it. Very critical. What's the total? That is, how fast is it? It's going this fast that way, and it's going this fast that way. But how fast is it really going? Well, it's going now, it doesn't mean this is not position, so I'm not traveling from here to here. My object here, my bird, or whatever that thing is, bee, dragonfly, is flying that way at that instant, that fast. How fast is it? Well, it's 6 squared, 6 meter per second squared, plus 4 meter per second squared, square root. That's how fast. What angle? Inverse tangent again. If this guy is, what did I say? 6.0 meter per second. And that's my V2y. And my V2x is negative 4.0 meter per second. Then this angle, call it theta. The tangent of this would be 6 over 4. Tangent theta equals meter per second over 4 meter per second. Use the absolute value. You see the units go away. It's 6 over 4. So, So what's the angle? The angle is the inverse tangent of 6 over 4. 6.0 over 4. You want the other angle? You want this angle? Fine. Then it's going to be the inverse tangent of 4 over 6. It doesn't matter, just as long as you clearly specify it. So the magnitude, or how much displacement, speed, in this case force, is given by Pythagorean theorem. The direction, draw it, see it, and use the inverse tangent to find either angle. Either one's fine, or the one that's asked for. So you can see how you would do this with a force. How strong? 2 squared plus 5 squared square root. in what direction, sketch that. Sketch that, those are the two short sides of a triangle. Use the inverse tangent and get either of those angles and specify it and show it. And that's how you go from being given component form into polar form, which really, in terms of what you want, what really matters, it's like how much and in what direction. That really tells you a lot about that vector. But in order to work with these vectors, to add them and subtract them, you have to take the polar form and break it into parts. Because in order to add or subtract vectors, you have to add or subtract all the parts in the x of all the vectors. And then separately add or subtract all the parts in the y direction. Get that combined. Then you've got a combined solution in component form, and you can find out what the result is by the Pythagorean theorem, inverse tangent. I hope that was clear, and with examples it will be. So let's go from polar form to component form in the next video.